This video will move into section 7.2, where we will discuss solving trig integrals. Now, this is not so much a new strategy, it's kind of pointing out some old techniques, some old manipulations that we've done with trig functions. I spend a little more time reminding us of some stuff that we probably should have had some experience with from Calc 1. When you get to the problems in the book, they focus a little bit more on using the trig identities. But all this, when we talk about trig integrals, we're referring to integrals that only contain trig functions. So if we're talking about things like x sine x dx, that's an integration by parts. That has a trig function, but the x is not a trig function. So, something like that is integration by parts. Something like that is now a U-substitution. So, again, we've seen trig functions come up in other places. They come up mixed with other functions. We've seen them mixed with e's and log functions. But again, for this section, we're talking about integrals that only contain trig functions. So, before we get into stuff that's slightly new, the first thing to remember is that we already know so many antiderivatives. So just reminding us of our f prime chart, we have our basic 6 trig functions here and their derivatives. So therefore, antiderivatives, these 4 in the middle, these are somewhat complicated and ugly looking, but as long as we know our chart, they are known antiderivatives. So those look ugly, but are not that bad. The top 2 are especially nice. We see sine and cosine come up all the time. And then a reminder, I believe it was section 6.4, we learned these 2 antiderivatives now that we had logs at our disposal. Here we prove this by writing tangent as sine over cosine and letting u be the denominator. We ended up getting this with a little, log identity. We initially had negative the log of cosine, but brought that negative in as an exponent. This one was even tougher. We ended up multiplying top and bottom by secant plus tangent, just so that u equals the denominator would work. And then this is where we're going to stop, everybody. We could easily add cotangent and cosecant and do the same things. For cotangent, we'd rewrite as cosine over sine, u is the denominator, and that worked out very clean. The log of sine would have a derivative of cotangent. And then for cosecant, we'd have to multiply top and bottom by cosecant plus cotangent. Similar things would happen. We'd end up getting negative out in front, the log of cosecant plus cotangent. But pointing that out so that if it ever came up in the future, you could find those antiderivatives and use similar techniques. But you also notice the book really focuses on these 2 a lot more as well. They kind of give you a little bit of a break with cotangent and cosecant, because what we are going to see in this section, there are a lot of interesting ways to pair the trig functions. And then when it comes to derivatives, antiderivatives, sine and cosine have a very nice pairing, a very nice relationship where they work well together. Secant and tangent actually have a similar relationship. And then cotangent and cosecant also have that same relationship. So you'll notice when we start getting to work here, we'll do a lot with sine and cosine. We'll also do a nice chunk with tangent and secant. But then we'll kind of just point out that the things we do with tangent and secant, we could do similar things with cotangent and cosecant. So all this, especially if we're meeting in person, trying to keep this list so it's not so overwhelming, so massive. But even from working at home, you could access other problems to kind of remind yourself, but still trying to keep ourselves not to overwhelm us with all the facts that we need. Because what we are going to do in this section, the real key to solving trig integrals is first, again, knowing your basics. So knowing when you're in a tough spot versus when you're not. But then second, using trig identities to manipulate to get to one of these better forms or to get to a spot where we will use a basic U-substitution. It'll be u as the inner function, and then we use power rule for the antiderivative. That's the direction we're going. What identities are we going to use? Well, again, there's a lot of your basic trig facts. Just going to throw this old page up very quickly as a reminder. All of your basics, converting trig functions to sines and cosines, those are an absolute must. Those are definitely going to come up. But then on top of that, we use the Pythagorean trig identities quite a bit. So we have the Pythagorean trig identity, sine squared plus cosine squared equals 1. For some people, they like to write the other forms of this, that you could solve this for cosine squared by subtracting and have 1 minus sine squared is cosine squared, or similar, sine squared equals 1 minus cosine squared. Those are really the same identity, just some gentle manipulations. Certainly can copy those three down. We will use all of them and are going to use them quite a bit. But now we can really take this and manipulate this into two more different trig identities. If I take this identity and I divide everything by cosine squared, well, sine squared divided by cosine squared, that would give me tangent squared, right? Sine over cosine is tangent, so sine squared over cosine squared is tangent squared. Plus, here, cosine squared over cosine squared cancels, gives us 1. 1 divided by cosine squared would give me secant squared. See, here's an extra catch I didn't say a moment ago. I pointed out that the derivatives and antiderivatives in sine and cosine really cross over and work hand in hand together. But then we also have this identity where we could always convert sines into cosines or cosines into sines. Now, this identity, the manipulation of this into this, again, you could still play the little games. Tan squared plus 1 is secant squared. Subtract the 1 over, tan squared equals secant squared minus 1. But those manipulations, that will allow us to convert secants and tangents back and forth into each other because, again, their derivatives and antis are also closely related. Go back to the top and now divide everything by sine squared, and we'll get the last piece here. Sine squared over sine squared is 1, plus cosine squared over sine squared is cotangent squared, and then last, 1 over sine squared is cosecant squared. So again, we still may use this. You'll see just in the basic manipulations, this may still help us, but as we get deeper into the section, these two are going to be the ones that get a little more use. But we definitely need to be familiar with all of these so that we can use them as necessary. Now, why are these necessary? Let's start solving some trig integrals. And like I said at the beginning, instead of just jumping into kind of the newer, the harder stuff that forces us to use these identities in some newer creative ways, there are more basic ones we can start with. The other thing I can point out, I will mention quickly, it's not just the Pythagorean trig identities that get used. Again, there are lots and lots and lots of ways to manipulate the trig functions. The book also mentions the double angle formulas, and I'll quickly mention that. The book also shows these formulas to convert sines and cosines when the angles don't match, right? We can only combine things like this, sine squared over cosine squared is tangent squared, because they have the exact same angle. If it was sine of 2 theta over cosine of 5 theta, well, then they don't become a tangent. They have to have the same angle. So there are other formulas for things like if you have sine 3x cosine 5x, well, you can manipulate that into, I believe it's something like sine of a minus b plus the sine of a plus b, where a and b are the original angles. So again, the book really shows us lots and lots, but what we are going to primarily focus on are the basics of trig integrals and then the ones that involve these identities used to manipulate. So we're going to jump right in, and we are going to start evaluating integrals. And just like we saw in 7.1 and what we will continue to see is that these are antiderivative techniques. So the book may stick some definite integrals in and has lots of indefinite integrals. I'm going to really focus on the indefinite part, just getting the antiderivative. But for any of the homework problems that are definite, just put your bar in and don't forget to plug in your bounds. So the first one I want to start with initially looks pretty ugly. If we start off with 5 secant squared minus cosecant theta cotangent theta plus 7 tan theta d theta. If we look at this the wrong way, this can look like a really ugly and difficult integral. We've got 3 big pieces separated by addition subtraction, and at least that part is good. Now I could take the antiderivative of each piece separately, but inside each of those pieces, this has an inner outer. If you move too quickly, you might try a U-sub, but it's not necessary. It's a known antiderivative. Same thing here, ugly multiplication. But before you start multiplying or trying to manipulate or U-sub, again, it is a known antiderivative. And then even here, before we got to chapter 6, that doesn't look tough at all. Doesn't have any inner outer, doesn't have any multiplication or division that's in the way. But before last chapter, it wasn't on our chart. Now it is. So that's the first thing. We still want to analyze our situation. This is what I was talking about at the beginning. When we talk about trig integrals, everything here is a trig function. No regular variables, x's or thetas. There's no extra, e's or logs or anything like that. Just pure trig functions. That's what we're referring to in this section. So again, looked ugly, but we know our basics. We're doing each one of these separately. Here, the 5 pushes along, and the anti of secant squared is tangent. Next, technically, some people push the minus along, and then the anti is a minus cosecant. Others, whichever way you think of it, but this antiderivative doesn't have an extra number and takes me straight back to cosecant. I got to have something that connects these two, so that has to be a plus sign. Always, even though we're focusing on the antiderivative, can always just quickly check our work, everybody. It's so quick to just go along and just double check. Yep, the derivative of tangent is secant squared. Yes, the derivative of cosecant is negative cosecant cotangent. So everything just confirming that what we've done so far is correct. Plus 7 pushes along. And now this one looks a little ugly, but it's just log of secant. Again, certainly can check with the derivative. 1 over secant times the derivative of secant, secant tangent. Secants would cancel, and you're left with the tangent. So, look pretty ugly, but not bad at all. Number 2. Number 2 is easier, so to speak, but again, still looks a little tough. If you ignore exponents, you're in big trouble. People who look and see 2 pieces separated by addition, and then they just go to the chart and go like, well, the anti of sine takes me back to cosine. Technically, positive sine would take me to negative cosine when I take my anti, but that's ignoring the squared here. And you can't ignore it, right? It's got to be that perfect. This antiderivative here led me to here because it was a perfect secant squared goes back to tangent. Not secant cubed, not secant to the first power. Those would be completely different antiderivative. So we can't ignore exponents like that. So these are not simple antiderivatives. These are not simple antiderivatives. I can't ignore that exponent. But here, this is where that first identity pops up. And this one, this is definitely staring at us right in the face. That identity is there. That identity definitely simplifies things. Here, just the silly little thing people do after they make that identity, we've clearly got things into a better situation, right? No more inner outer. Instead of 2 pieces, now there's only 1 piece and it's a simple piece. Just one little thing, just don't miss the variable here is theta. So the anti of 1 is not x here. The anti would just be theta plus c. So still, not too bad. You know, again, that identity, that's got to be really, really obvious at this point. And maybe through Calc, when you've got some experience, this section, you're going to get a lot of experience with the identity. And again, this is the best form. This made things so easy. Definitely was a very, very quick, simple manipulation to get to a good, easy antiderivative, and you're done. But now number 3, now we're starting to get a little more complicated. Let's do 1 over sine squared plus cotangent theta sine theta d theta. Now we're starting to progress a little bit more. And you know what, actually, let's even make this a 1 minus here. 1 over 1 minus sine squared. Let's do that. And one other very quick thing before we finish this problem. Let me bounce back for one quick moment. Derivatives versus anti. I cannot tell you how many people just run around the same circle here and here. They see secant squared, they say the antiderivative is tangent, and that part is correct. But then they get here and they see tangent, and they give the anti as secant squared. No, no, no. The derivative of tangent is secant squared. The antiderivative of tangent is log of secant. So just as we're using this chart, and as we've seen with integration by parts, or as we'll eventually get to some U-substitutions, even though big picture you're taking an antiderivative, derivatives do come up. So just again, be very careful with your chart. Make sure when you're antiderivative, you're right side to left, versus when you're taking a regular derivative, it's left to right. So just to avoid some of those mistakes, just that quick little warning. But now let's get back to number 3. Now I've got 2 pieces, but now it's just really, really starting to get to be a mess. There's no easy, well, these are known antiderivatives. Neither of these are on our chart the way they are, the way they stand. There's no quick identity like we saw here. Well, that's obviously can be replaced with a 1, and now that makes it much easier to finish solving the problem. So here, now we've got some more work to do. So certainly still at least recognizing there's 2 pieces here. So treating these as 2 complete separate antiderivatives. And I know sometimes people don't write the d theta, but it's a good habit because you may need u subs, and a u sub here may not be at least the same as the u sub that may go here. So just to make sure you're fully set up, you're solving each of these as 2 completely separate integrals. And right off the bat, this is that second manipulation of that main identity that we just looked at here. As we said, sine squared plus cosine squared, that has to be obvious. That is 1. But this almost has to be just as obvious. That I realize that, hey, 1 minus sine squared is the same thing as cosine squared. Now, is that the right move to make? Maybe. I don't know quite now because I still see division, but now, well, 1 over cosine is secant, so 1 over cosine squared is manipulated and just became secant squared, and now I know I'm on the right track. I don't just manipulate for the sake of manipulating, I'm manipulating trying to get it to be something that I know. And this is a known antiderivative. So the anti of just the first part is tangent. Plus, now I come over here. Well, this is not one of those Pythagorean trig identities that we were discussing at the top, but one of the other things to definitely remember are your basics of sine and cosine. To remember that if your trig functions don't match, like if this was cosecant times cotangent, just like we saw up here, well, that is a known antiderivative. And again, don't let the order bother you. If this was cotangent times cosecant here, it's the same thing. You're multiplying the order a times b, b times a. It's the same thing. So that was a known antiderivative. If that was cosecant, it would also be a known antiderivative, but it's not. So what else can I try? Well, one of the other big basics is trying to get things back to their most basic form, which is sines and cosines. Cotangent is cosine over sine. So recognizing that, and now realizing, hey, algebraically, I can cross those off. And now I'm just left with cosine. So here, it was some identities and a little manipulation to get to a known antiderivative. Here, same thing. Little manipulation, little identities to get to a known trig antiderivative. This final answer definitely wasn't obvious at the beginning, but through some manipulation, both of these are simple pieces, and our answer is tangent plus sine. Okay, similar, number 4. Number 4, let's look at sine divided by cosine squared. Again, sine and cosine, we're going to see, work really, really nice together. There is an alternative way to actually solve this problem. Believe it or not, a u sub of u equals cosine would solve this problem. But without using that, again, that's where we also said in this chapter, while we almost outline each section, like integration by parts was for multiplication of simple functions, or when we had a function, one function with a known derivative but unknown anti, and now we're talking about trig integrals, but U-substitution still come up. Again, everything we discuss, there's going to be some overlap. There are some problems where one technique is definitely going to be our best way, but there are some that a variety of things would work. So one more time, you might look at this, see complexity here, see division, see inner outer, and say, hey, u as the inner piece. And again, you can make some progress here. U is cosine, the derivative would be negative sine, you get a cancellation, you get a -1 over u squared. Again, you still have some work to do, but you're making progress. You've simplified the function, and you've moved from something complicated to something better that you can continue to work on and solve by hand. But now, back to this one. A funny thing, after number 3, we realize that rewriting our trig functions as sines and cosines can help, but here they are already sines and cosines. So here my next reminder is just that anything I give you, you do have a way to solve. There's got to be some way this is going to work. So maybe if you didn't see that possibility for you, maybe you just play a little bit with this. You look at this a little bit more and you say, well, let's see. If I break this up a little bit, just breaking up the cosine squared into cosine times cosine, and now treat this like 2 separate fractions. Sine over cosine is tangent, and then this second fraction would be 1 over cosine, which is secant. And hey, we're back on our chart. And just the way I happen to break this up, I wrote it as tangent times secant, but on my chart I have secant times tangent. But again, same thing. This has an antiderivative of secant. By the way, if you do that u that I was talking about, you end up with u to the -1 power as your answer, and cosine to the -1 power. Don't mistake that for inverse cosine. Cosine to the -1 is secant. So that u sub, of course, it's the same integral. We better end up with the same answer at the end. But again, everybody, 1 through 4, technically outside of just having that tangent in number 1, just that tangent piece all by itself, but everything else, we could have done this since Calc 1. All this still goes with the basics of our chart, with just basic trig manipulation. And actually, same thing with number 5. But number 5 will start to lead us to what's a little bit new in this upcoming section, in 7.2. Because in number 5, this is an ideal trig integral. And like I said, this can kind of come back and you could apply this to number 4. So if that U sub I mentioned wasn't something obvious as something to try, if this was not obvious, which I don't think this was, that was definitely something else to try. And I think more of us would have thought of this here just with the old basics of U. And that same thing applies here. Here we had division that we really couldn't clean up. Again, we kind of could through trig manipulation, but no direct. Sine and cosine don't cancel or anything like that. So we had that division and we had inner-outer. U as the inner is worth trying, and that works here. Well, this is almost the same thing. Sine times cosine cubed. Now we've got multiplication instead of division, and over here I've got my inner-outer. So once again, U equals cosine seems like it'll work, and it will. Hopefully we're getting better with our U subs. A lot of practice came up in chapter 6 here, so hopefully we're getting better. So even right now, I'm feeling good about this U sub. By picking U as the inner piece, the du is going to cancel with this extra piece. Let me see it happen. Sine's hanging out. This became U cubed, and then the d theta, du over negative sine. Just as we suggested, the signs do cancel. I do have this extra negative. And, technically here it's in the denominator, but it's just a negative sign, a -1. Denominator, numerator, all the same thing. And now I can take the anti, and I can back sub. As always, everything we've done, take the derivative, check your answer. But now, the one little catch with that, in the earlier problems, if you did not manipulate correctly, well, then you would not be able to check. If I did wrong manipulation to get here, yes, I could check the derivative of this is this, but if I manipulated incorrectly to get here, I wouldn't be able to catch that by checking with my derivative. But here, I didn't do any manipulation at all. I went right into my U sub, so this will definitely confirm. Take the derivative, 4 times -1/4, you get a -1, cosine cubed, times the derivative of the inner, a negative sign. That extra negative and that negative is a positive sign. And there is your sine cosine cubed. But once again, everybody, that was still more of an ideal situation. Because if you go back, especially if you really focused on our textbook, I know a lot of people use a lot of outside resources, but when U-substitutions were introduced in chapter 4, our textbook, even though it mentions the idea of U as the inner function, it always started off with this idea of looking for this setup to pick your U. That if you saw, here was the inner-outer that we're talking about, and specifically, U equals the inner work because you see the derivative of that inner piece somewhere else in the integral. So that was always our motivation. How do we make good choices for U? Well, other good things have to happen, but definitely when you see the derivative of that U, that is a good choice. And that's exactly what we have here. So the idea with some of these ugly, fancier trig integrals is to have one trig function to a power and the derivative of that trig function sitting next to it. That's why I made this extra note on our chart, everybody, because that's where so many of these U substitutions are going to go. They're going to work just like this one did. There was my trig function to a power, and there was the derivative of that trig function. That's not the derivative of cosine cubed. It's the derivative of just the inner part, just the cosine. And again, we're not worried about the extra negative. That's good enough. We can make that work. So that's really what we're looking to do. And that's what, again, that's why these were both more of the ideal U substitutions. But now let's take a look at number 6. And how different things are. The only thing that looks quickly different from number 5 to number 6 is that now sine is also squared. But now we don't have that perfect scenario anymore. Because now, again, if you go too quickly, you can make the mistake and say, well, if u is sine, the derivative is cosine. But you don't just have one cosine here, you have 3 cosines. And then vice versa, if u is cosine like we did up here, well, the derivative is sine, but only one sine cancels. You need all the other functions to cancel. So how do we make this one work? The answer is we manipulate. We try something. And this is where I actually don't like that our book gives us 2 separate boxes. One for the sine and cosine combinations, and another one for the tangent secant combinations. Like we mentioned earlier, those are going to be nice pairs that go well together. We already saw how nicely these have gone well together. And even though this one's not working out quite as nicely, we will see that it's still going to work pretty nice here. So, how do we get this to work? We want that ideal U-substitution. And again, instead of what I was trying to say, instead of memorizing those boxes in the book, let's just manipulate until something works. But what do you manipulate? We'd like something like this. So if you want to try converting sines into cosines, sine squared would become this. So my integral, I'll distribute this out, would be cosine cubed minus cosine to the 5th. And that's not any better. Okay, I forced a manipulation. It's not as nice as what we were seeing earlier when a sine squared plus cosine squared, that obviously should be replaced with a 1. A 1 minus sine squared likely will be better if we replace it with a cosine squared. But here, I'm forcing, that's not as obvious to make this move, but I'm just trying something. There's got to be some way we can make this work, so I'm trying something. But by making this conversion, this is no good. Because now you might say, hey, yeah, try that u sub, but now you don't have the extra sign to cancel. And that was necessary in number 5, so this is no good. Well, what else can we try? Here's the better piece of advice, everybody. We want to expect that we want that extra trig function. So with a little practice, this is the better one to manipulate. Let's make this into cosine times cosine squared, and then the cosine squared we will replace with this. So this is getting a little messy. So let me rewrite everything now. I still have the sine squared. Cosine cubed, I left one cosine behind, and then the other cosine squared I'm replacing with the identity 1 minus sine squared. So sine squared, cosine cubed, where this was cosine and this was cosine squared. And now at first glance, you may say, wow, this really, really looks big and ugly. And some people, they make their u sub right here. I prefer to multiply this out first. So sine squared cosine times 1 is sine squared cosine, minus sine squared cosine times sine squared is sine to the 4th cosine. Now this is the first one we're doing together, but with practice, you'll realize initially this may look worse. We started off with a little bit of a mess here, and now it almost feels like this mess is worse, because now I've got 2 big pieces. But if you look carefully, even though there's 2 pieces, we're in that ideal situation here in both of these that we were up here right off the bat. That now I have one trig function to a power, both of these it's sine. Here it's sine squared, here it's sine to the 4th, but in both of these, sine is being raised to a power, and the derivative of sine, cosine, is sitting right next to it. Now, it doesn't matter if that extra sitting next to it is in front or behind, but that it's there ready to cancel. So both of these, and now, again, another little personal preference. Some people, even though you're doing the same U-substitution, Some people would rather do these as two separate integrals. So get your integral sign in here, get an extra d theta in over here. But I'm going to realize that, again, the same u works for both. That if I let u be sine, du would be a clean, perfect cosine. So in both of these, this just became u squared, and there's your du. Cosine times du over cosine, you get your du. And the same thing here. Sine to the fourth is u to the fourth. Cosine d theta, well, either right there, cosine d theta is du, or as you solve, cosine theta times du over cosine, you get your du. 2 times we ended up with this, because again, that's what's going to be so common here. If we're only dealing with trig functions, we'll get u as the trig function. Our antis, u cubed over 3 minus u to the 5th over 5. Again, if this was a definite integral, put your bar, but as an indefinite plus z, and I'll back sub. You know, little things, some people still would rather write sine cubed over 3, but for some reason, a lot more people prefer this. Instead of writing cosine to the 4th over 4, they'd rather just put the fraction out in front. So I'll do that here as well. So this will be 1/3 sine cubed minus 1/5 sine to the 5th power plus c. Again, if you take your derivative, that'll only confirm you're right to here. So if you did any manipulating mistake or foiling, distributing mistake, you wouldn't catch that by checking your derivative. That would only confirm from here to here that everything you did is correct. Okay. This is a tough section, everybody. Some people very quickly, because through the previous work, they've already had a lot of practice with U-substitutions and they feel good. Some people pick up on this very quickly. Others, this takes a bit more. This is definitely not the easiest thing to do, so let's just keep getting more practice. Next, number 7. Let's look at the integral cosine cubed. Now, I do like to speak about experience, but I hope you're starting to realize subtle different changes in these trig problems can make for very, very different experiences. Again, go back. Number 5, sine times cosine cubed, was perfectly ready for a U substitution. But make that sine squared times cosine cubed, and now you've got a lot more manipulating that needs to be done. So now in number 7, now there is no sine function at all. So one more time. It's not a known trig antiderivative. We do have some inner-outer, but if you just try u as the inner, you'd have a du of sine, negative sine technically, but no extra sine term to cancel. So I've got to manipulate. That's the biggest thing, everybody. What is section 7.2 about? It's about getting good practice manipulating trig integrals. There's no real new technique we're learning here. There's no new formula like integration by parts, or as we get to the later section 7.3, 7.4, new ideas. This is purely just taking things further with more complicated trig integrals, pointing out how more of the identities can be involved in the problem, and getting practice so that you realize when you're in a good spot and when you could just take advantage and solve either directly or with a U-sub, or when you're not in a good spot and when you need to manipulate. And that's what I have to do here. So again, I've just got to do something just to do it. So I'm going to rewrite this as cosine times cosine squared. Why am I doing that? Because I can look at the cosine squared and I can manipulate that into 1 minus sine squared. And now if I distribute that out, and all this, everybody, I'm just trying. I don't know if things are good or bad yet. Right now I'm just trying. And after this line, now I'll have a better way to evaluate how well it's going. So I'll distribute it out just like I did in the last one. And again, I will point out some people right here, They just do it right off the bat. They don't write it as two separate trig integrals. They just right off the bat, there's your u, there's your du. The cosine factors out of both and cancels. So there are little minute differences. Some people, how they algebraically want to manipulate. So don't let those things bother you, everybody. I will distribute again. So I'll get cosine times 1 minus cosine times sine squared. And through this manipulation, again, just like the previous one, now there's two pieces instead of just one piece, but they're both better. This is nothing fancy at all. That's not even a U-substitution. That's a known antiderivative. The anti of cosine is sine. Over here, though, a little bit tougher, but another good situation. Put my integral sign in here. Don't lose that, right? Just working on this piece right now. And one more time, I see multiplication, I see inner outer, but once again, it's that good situation. One trig function raised to a power, and the derivative of that trig function sitting right next to it. This will be a u is sine, so du is cosine. That will become minus the integral u squared du. So you'll get that as your antiderivative. And when I back sub, there is my full answer. So let's continue here. Number 8. Now I could do, as I move into number 8, let's look at the integral cosine to the 5th power. This is just more from number 7. And I could do the same thing with number 6. If we did sine squared cosine to the 5th power, it will be very similar. What am I going to do? I'm just going to do what we did up here twice. Because now hopefully we're starting to get a little better. And now, after just doing a few more problems, now maybe it'll make a little more sense if you read the box that talks about sine and cosine. And the ideal is to have one of them to an odd power. Because as an odd power, like cosine cubed or cosine to the 5th, as an odd exponent, you could always break that into even exponents that could cleanly be converted with one trig function left over to cancel with the derivative. So that's the same thing that would happen here. I get cosine times cosine squared times cosine squared. I'd have to multiply all of this out. I'm going to do this a little fast, everybody, because here we'd have a minus 2 sine squared in the middle, so I'd have a minus 2 cosine, sine squared, yep. And then we'd have a plus sine to the 4th, so I'd have a plus cosine sine to the 4th. And you can finish this on your own. Realize we're basically in the same situation we were right here. This one, just like this piece here, is completely ready to go. And then you'd have two pieces here, but they're both just like this one. This one just has the extra 2 out in front and is the exact same. This one, well, it doesn't have the extra 2, but both of them have that trig function to a power, the derivative sitting right next to it. So that U-substitution will work on both of these. You get minus 2/3 u cubed here, plus 1/5 u to the 5th here, and then you would back sub. So, again, hopefully by doing several of these, you realize that to use those original Pythagorean identities, you needed to have squares. Sine squared can become cosine squareds. Cosine squareds can become sine squareds. So by breaking them off as squareds, those make for clean conversions, but we need that one extra by itself. Well, then that naturally leads to the question, what happens if they're only even exponents then? Now we just need a different identity. The book does this, I think it's example 3 in the book, does it with sine squared. I'll just show you with cosine squared. It's almost the same thing. It's just a different formula. we have other formulas. Again, lots and lots of ways to manipulate the trig functions. And one way to do that is that sine squared is this formula. This really comes from the double angle formula for cosine. And then similarly, cosine squared would be this. The big difference in these formulas, again, this was a double angle formula that had 2 theta and then went back to theta. We're just using them in a different way. So cosine squared, you'd use this identity. I'll distribute it. So I get 1/2 times 1 plus 1/2 cosine 2 theta. Don't overthink that. 1/2, a number, antiderivative with respect to theta. If it was an x, it would be 1/2 x, but it's a theta, so 1/2 theta. Here, some people would use a very little basic u sub here. But remember, how do you take a derivative and get cosine 2 theta? You must have started with a sine 2 theta. But this would have an extra times 2, but it's got a 1/2, so it needs a 1/4 to keep that balanced. I know I did that pretty quickly, everybody. I would not put that on a test, but it's just a quick reminder that you do have the exact similar one for sine squared in your book. If that ever came up, like if you're in differential equations, that you have this one in your notes, sine squared is already done in the book. It's just a different identity. If it was cosine to the 4th, you'd use the identity twice. That's all. Cosine squared times cosine squared. You'd FOIL this out. You get a cosine squared 2 theta. You'd have to use the identity again. That's all. So you'd just be an exercise in using the identity over and over. Okay, so lots of sines and cosines so far. So we see how they work nicely together and how we can manipulate one into the other. And now we should realize that tangents and secants are a little similar. Number 10, let's look at the integral tangent cubed secant squared. Initially, this looks pretty rough, similar to number 6. Initially, when we looked at number 6, that was definitely pretty rough as well. But to be clear, number 10 is actually one of those ideal situations. May not see it right off the bat. It seems right off the bat that it's very messy. It's not a known trig antiderivative. Again, plain secant tangent is a known antiderivative. But tangent cubed, secant squared, nope. And we can't break them apart. I can't just focus on the secant squared and say, well, that has an antiderivative of tangent. I have to take them together. But here, and honestly, this would actually work in both directions. You can let u be secant, but that would be a little clever, and then you'd actually need another identity to make that work. But this one is perfectly situated for u as tangent. I know I said earlier, one trig function to a power, and here we see both trig functions raised to powers, but listen to the full statement. One trig function raised to a power, any power, with the derivative of that trig function sitting right next to it. This is the derivative of this. So whether this was tangent cubed, tangent to the 5th, tangent to the 10th, the square root of tangent, any of those, there's my trig function to a power, and I'm not worried about this being to a power because that is the exact derivative of that trig function. This is a perfect u sub So again, ends up being, tangent to the 4th power, ends up being a fairly simple antiderivative. Is it always that easy? Well, no, not exactly. But especially when we realize we're dealing with tangent and secants, we're not just looking for a perfect secant or a perfect tangent, we're looking for the perfect derivative of that function. So secant squared is perfect because that is the exact derivative of tangent. You keep going. Let's just make this one a little more complicated now. Number 11. Let's look at tangent cubed secant to the fourth power. Now we've got to manipulate more. Because now, and this is where starting to think ahead is nice. The very beginning, we pointed out that, actually, I'll show you both of these, because this, again, can work pretty nicely in either direction, but you've got to start manipulating. Maybe you could start to think in your head a little bit, well, if u is tangent, du is secant squared, and that might motivate you to break up that secant squared into secant squared times secant squared, so that way the second secant squared can be converted into tan squared plus 1. Tangents, more tangents, and the derivative of tangent. That setup, I multiply it all out, I get secant squared tangent to the fifth power plus secant squared tangent cubed. And now both of these are perfectly situated. Again, they still look like a big mess, but they both have tangent raised to power and the derivative of tangent sitting right next to it. Both are perfectly set up for u is tangent, so that you will get u to the fifth and u cubed, so the antiderivative not bad, but not obvious. Maybe some of us were lucky enough to see that. Maybe some of us just multiplied it out, and it wasn't until we got to this line that we started to realize, hey, this could actually work. But you only realize this could work with good experience after seeing a problem like number 10 to realize this is a good situation. But again, there is an alternative here. I did not do this with sines and cosines, but we easily could, and there's at least one in the book where this would work. If in number 6, if I made that sine cubed cosine cubed, either one of these would have worked. I could have made cosine squared, convert those cosines into sines, and had the leftover cosine. If this was sine cubed, sine times sine squared, and I'd have the leftover sine. So sometimes you're lucky in that they both can work. And that happens here. If I think about u being secant, well, the derivative is going to need a secant and a tangent. So with that thinking, let me kick one tangent by itself, preparing for that. The other two tangents, tangent squareds, those will be converted into secant squared minus 1. And then we still have the secant to the fourth at the end. Put these together, multiply it all out. Tangent times secant squared times secant to the fourth. I get tangent secant to the sixth minus tangent times minus 1 times secant to the fourth. I get tangent secant to the fourth. This is still not quite as obvious because a lot of people will still say, okay, but wait a second, now you're missing the secant. Take one secant from each of these. Kick a secant next to the tangent, and then you have secant to the fifth, and this will become u to the fifth, minus. Kick a secant here, your tangent secant will now cancel. Secant cubed becomes u cubed. And now we back sub. And you might say, well, wait a second, these are slightly different answers. More trig identities. Again, you could always just take the derivative to check, right? We could always just check in that sense that here, take a derivative, 6 cancels, tangent to the fifth, the derivative tangent is secant squared. And, again, just to see that this derivative matches here, this derivative matches here. but to get it back to the original would need a little bit more manipulating after we get to that point. So, number 11, just stretching that idea of just when are we in a good situation versus when we're not, and if we're not, we'll just manipulate until things are in a good situation. So let's just finish up with a couple more here. Okay, let's go to number 12. And for number 12, let's take a look at tangent squared. Okay, tangent squared all by itself. Again, you got to do something here. It's not a known antiderivative, so you do something. You apply the identity. Tangent squared is secant squared minus 1. And now, again, that identity, just trying to point out, after number 11, manipulating, and then some fairly heavy-duty U-subs, no matter which way you did that, that was pretty tough no matter what. But now all of a sudden you just do that identity, and now you're done. The anti of secant squared is tangent, and the anti of 1 is theta. So this is another one that just applying this identity kind of immediately moves us to a good situation that we can solve. If it was tangent to the 4th power, well, try it once. Before we just substitute everything, right? We shouldn't try and make massive manipulations. Let's try and manipulate little bits. So instead of just doing this identity twice, which actually wouldn't work, let's start off. Tangent to the 4th is tan squared times tan squared. The second tan squared, I'll apply that identity. Now if I multiply that out, I'd get tan squared secant squared minus the integral tan squared. This is a good one. U is tangent, the derivative is secant squared. You should be able to confirm this. You would let that your U be tangent, you get a U squared, you'll end up with U cubed over 3, so that'll give me 1/3 tangent cubed, minus the tan squared. Well, then we'd go do this work up here. So we'd end up getting minus tan theta plus C. So again, just manipulating, just trying. If this was tangent cubed, we'd have tangent times tangent squared. This still works. Tangent times secant squared. You would get U as tangent. Now you'd only get U squared over 2 at the end, but that same thing would work. Minus tangent when you distribute. It wouldn't be tangent squared, it would just be a tangent. And that would be a known antiderivative. So tangent squared, tangent cubed, tangent to the 4th power. The key to any one of those is to take 2 of those tangents and to use the identity to manipulate. Okay, last one. And we're going to end with a tough one, everybody. This one is specifically done in your book, but I wanted to show it to you because it is. It's definitely tough, not to make you feel like it's absolutely a must, but as we move along a little bit, this is almost certainly going to come up at some point. So just to have it in your notes as a place to go back. How do you finish solving this? Well, from what we've seen, going to try manipulating a little bit, but instead of going here and then thinking about, well, secant squared, I can make that a tan squared plus 1, I'd eventually just run around in some circles. Believe it or not, we're going to use integration by parts on this. I'm breaking this up in a very specific way so that I can let U be secant and dv can be the secant squared theta d theta. So you got to remember, go back to the beginning of chapter 7. What's the correct technique? It's the one that works. And unfortunately, sometimes it's, well, what works? Sometimes something works just because we just kept trying and playing with it and we got a little lucky. And that's the situation we're going to be in here. It's not quite an obvious integration by parts problem, but again, it'll work. Because if this is my u, du, secant theta, tan theta, d theta, and then the antiderivative of secant squared is tangent. So u times v minus the integral v du and just notice my v du, I just multiplied the tangents together to get tangent squared. And now, seems a little strange, but now I come here and I apply the identity. So this will become secant squared minus 1. Why do I do that? So I can distribute secant times secant squared. I get secant cubed minus secant. But don't forget this minus is out in front of everything. So that makes this a plus. And I'm going to treat these as two separate integrals. And now we get the big catch. This we know. This is what we started with. Add this to the other side. So I get 2 times the integral secant cubed. And we have secant tangent minus, and here the integral of secant is log of secant plus tangent. We have to divide everything by 2. And there is our final answer. Not at all easy. Ended up using an identity, but not right at the beginning. We ended up using that a little bit at the end. And there are other ways to solve this, but a really interesting problem, seeing how just because it was just a trig integral, sometimes integration by parts, just like we saw everything else, sometimes just manipulating through an identity, sometimes just trying with the basics of a U-sub. It can work, but you gotta have enough experience to realize, are you making forward progress or are you making things worse, in which case you should go back and try something different.